All right, so let's continue our discussion. So if you remember the last place that we went on was talking about and solving examples using working stress method or allowable stress method, both we can call that, on which we were focusing on the stress uh, that you're gonna reach as like actual stress in concrete and steel. We were making sure that the stresses are below the allowable strength that is coming from the material properties. All right. So also over there, we learned the concept of the gross moment of inertia and crack moment of inertia. So this was sort of like a preliminary design in a way, just a checkup, and it wouldn't be something really, I would say, uh, it wasn't something through. So we want to learn more techniques for more in-depth calculation when we are talking about the ultimate strength of concrete, for example. All right, so let's continue our discussion. So now we want to do the flexural design of concrete structure, all right, or bending. It's called bending as well, same meaning, right? Flexural bending analysis of concrete beam, like RC beam, all right? When a small transverse load is applied on a reinforced concrete beam, and the load is uniform, the load is increased until the beam fails, the beam will undergo three distinct stages before failure. All right, so what we're talking about is we are having this beam with this cross section, for example, right? B and H, okay? Okay. There is a loading applied on it. Okay. So we want to know, all right, we want to know how much we need to increase this W until it causes failure on the structure. We're gonna have crack, and this cracks propagate until that the structure, the beam would fail. All right. So we want to see like where would be that ultimate failure, like what phases we are passing through to reach the total failure of RC beam. All right. So three stages we are passing through. First, you are in uncracked region, meaning that you're healthy, you haven't cracked yet. All right, uncracked. It is not cracked yet. Then it is cracked. Okay. Elastic stress range though. It is still in the elastic region of concrete. Okay. So here I can add that WSD, the working stress method, or ASD, allowable stress design method, on which we use transformed area. Which we went through, right? We went through. So on this one, you would use IG, right? You would use IG, the gross moment of inertia. All right. And then you're gonna pass, still going through, because you know that the concrete wouldn't fail. What was the stress strain diagram for the concrete? So if you remember, you go up, you come down like this, right? So here is F prime C, right? So this is like a linear region, I would say. And then so you're cracked in this region, and then you pass through the elastic region, you go to the ultimate string, and you come down and fail around. If you remember, we said on the strain of 3000, we would assume the concrete would fail, would crush. Okay. So like a linear region would be here, as we discussed. And maybe the elastic region would be a little bit larger. All right. Okay. So when we are talking about the ultimate strength, right, meaning that we are going through the whole phases all the way. So everything is included at this point, right? So we want to say, all right, when everything is done, now what is the status of concrete? Okay, so that's what we are talking at this point. So ultimate string stage, ultimate string designer, we can call it probably. Okay, ultimate string design. All right. So let's look at the different stress and strain diagram on the cross section as we go through these three stages: uncracked, cracked, and ultimate strain stage. All right. Starting with uncracked stage. All right. So what's going on here? Small loads and no cracks in concrete yet. This is the stage we're talking about. Tensile strain, or sorry, tensile stress, tension. Why the tension part is more important for me? Why I'm just emphasizing on tension at this point? Why it is your criteria? Because it is weaker. We're gonna reach to that earlier. That is a weak point. That's why it would be our critical points for investigation. So tensile stress, less than margin of rupture, right? Your tensile strain that you're creating. So I would say FT applied, all right? It is less than the margin of rupture, which is a tensile strength of concrete in a way. Strength of concrete. FR. And you know how to find the FR, right? You remember that? 7.5 lambda square root of F prime C. All right. Or the moment wise, we can say the same thing, right? Your apply moment to be less than the moment that cause crack, which is corresponding to FR. These are two corresponding together, and these two are corresponding together. All right. So stress strain distribution essentially is the same. So let's just look at this distribution. All right. First, I'm talking about the strain. So let me draw a black line here. Okay. All right. So on the first, and this is on this one, I'm gonna draw the strain. Okay, if this is a cross section, you have reinforcement, you have a tension steel at the bottom and everything. All right. So if I want to have, if I want to show the deformation, if I basically apply bending or flexure in my concrete in the concrete beam. So as you have seen it before in your mechanics of materials, you are going to have some compression on top, right? Compression. The maximum compression deformation would be on the farthest fiber away from the neutral axis. You know that it's going to approach to 0, right? On the neutral axis, and then you're going to continue to reach to maximum tension at the other side, at the other end. All right. So this would be your status. Okay. Epsilon C for concrete or compression on top. Okay. Epsilon C for concrete, but tension at the very bottom. Okay. For a steel, this would be the strain, right? This is the level of steel. I'm going to show the epsilon S. All right. So this is your stress strain, or sorry, the strain illustration graph on the elevation of the beam of your cross section. All right. Now let's look at the stress. All right. So look at the stress. So what would be the stress graph? Okay. You show it with sigma, you can show it with f as well, the lowercase f, either ways. All right. So again, we are going to have maximum, because why we are saying the maximum, don't forget, we have this expression. Sigma is E epsilon. So if you multiply it by constant, you're going to find the stress. So if you have the strain multiplied by a constant, you're going to, so the shapes would be the same, right? So it would be having the same shape because it is a linear region and it is not cracked yet. Okay. So maximum compression on top. Okay. And here you have maximum tension in concrete. One side compression, one side tension, right? So if I want just a little bit compression on top, tension at the bottom. All right. Also, you are going to have the sigma for the sigma for the steel, on which you would say what? You would say Fs over modular ratio. Modular ratio. Because for the steel, you know that from mechanics of materials, again, when we have two different materials, we need to multiply the final answer to the modular ratio. Okay. So at this point, we know that we have a tensile strength in steel. All right. And also, in a way, we have in concrete, in that level, also we have steel level. All right. So if you think about it, there is a tension in a steel in this level, right? We need to use the modular ratio because you're changing material. Also, we can say this plane, it is like a concrete at that level. The stress in concrete also has a stress in that level, which is equal, right, at this S level. All right. So from both aspects of looking at the steel or concrete, we can talk about this level, this particular level. All right. So let's see. All right. So let me give you a note here. Since there is no crack in concrete, entire section can resist applied loads. All right. This is the uncracked situation. If you have uncracked situation, this would be the case. Next one, we're going to look at the crack section. In other words, elastic stress range when you are in the elastic region. All right. So let's see. Moment now become more than the cracking moment, or the tension is higher than modulus of rupture. right? So you're passing that threshold. The moment is higher than the cracking moment, or the tension, applied tension is more than the threshold of modulus of rupture. In other words, this is a tensile strength of concrete, right? Talk about it. Okay. Another assumptions we are making. All right, so let me put this way. Let me, before I talk about that, for this guy, I would say since the applied stress is more than FR, tension concrete cracks. All right. So concrete in tension region can no longer resist load. All right. So let me tell you what's going on here quickly before I go back and show you the strain and stress distribution and the elevation of the member. All right. So we discussed that on the top, we are dealing with, if you deal with the compression on top, tension at the bottom. So as soon as you crack, where, on which part of the concrete you will crack? Well, the cracking is going to happen here, right? On tension side. Why? Because it is weaker. That is a vulnerable place in concrete, tension. So it starts to crack, okay? So as soon as it starts to crack, right? So this portion of concrete that is under tension, it wouldn't work anymore. It wouldn't work anymore, right? Because it is cracked, it is gone. So the only compression side of concrete will work. That's what we are talking about. Only concrete in compression, which is on top, are good to go. But at the bottom, the concrete does not work for you anymore because it is cracked. Which on this case, as we discussed a little bit before, you're going to be dealing with steel to help you for tension. All right. So let's just look at it. What would be the graph? All right. So before going there, let's just see these guys as well. So the assumption we're having here is that, all right, the stress on the steel is less than its yield point yet. So you haven't yield yet on the reinforcement. You're still having strength in the reinforcement. All right. And your compression, right, it is less than half F prime C almost. It just, this half, what was the number, if you remember, it was like 0.45 for our WST design, if you remember, right? Because just we want to make sure that we are in the elastic region. So do not forget these two rules. These two, I would say, conditions. Why these two conditions are important? Because it is telling you that we are not reaching to the yield point yet. We are not in the yield point. Remember the graph one more time? This was the graph, right? So if you remember, I said, all right, almost like to this point, it will be your elastic region. Okay? So it's just trying to say that, all right, although we are cracked, but we are still here from compression point of view. From the compression point of view. Okay? We are not going all the way. We are not going all the way. It is not ultimate yet. All right. So let's look at the stress strain diagram. So it says once the tension region of the concrete crack, it can no longer resist any stress. All right. That's what we discussed, right? So let's look at the Let's look at the strain, and this one is stress. All right. For the strain, the deformation, well, you know that the strain would be, you're having concrete strain maximum on top. It goes to 0 on neutral axis. It continues with the other direction, like in tension, let's say. Okay. So it would be epsilon of a steel, right? This is a steel level. So somebody might say, all right, why you didn't go all the way to the bottom this time? Why you just stop in the steel level? I'm pretty sure if I was in class, some of you would already know that. That's why I'm not going all the way to the bottom, because don't forget here, it is crushed. The concrete crushed. Not crushed, sorry, it is cracked, right? It is cracked, so it wouldn't take any more stress for you at the bottom on the tension region, all right? So that's why until the steel would be important, the deformation, the stress on the steel would be important for me. Okay. So something we want to basically also pay attention on this one is that the epsilon at that you steel, you see in the steel, I'm going to say applied deformation or strain, it is less than your yield strain. We haven't reached, as we discussed here, we haven't reached the yield point. This is the same for the strain. We haven't reached the yield point strain wise on the steel as well. All right. So this is the deformation strain. What about the stress? On the stress, you're having maximum on top because you're following really what the stress tells you. So FC on top, okay? So you have a linear change. Why linear? Because you are at the elastic region. So there's a linear relationship here. There's a really linear relationship between the stress and strain at this point. Excuse me. All right. So as I told you, there is nothing going on stress-wise in concrete. So we don't care about the concrete. The only thing you care at this point, you're going to say, on the steel level, I'm having stresses apply on the steel. I'm going to call it Fs. All right. Okay. So this would be the way to show the stress. Okay. So let me do the talk here. A little bit about it cracking concrete, cracks. In the region, I can spell it, where M is more than M crack. All right. So what does it mean? Let me show you a concrete beam. All right. This concrete beam is under distributed load. Okay. So if we want to show the moment diagram, it would be like this, right? The moment diagram would be like this for simple supported beam with distributed load, all right? So as you can see here, the moment, apply moment would be different, right? For example, cracking moment probably would be land here, like value-wise. So it is cracking moment, right? So on these regions above that, you're gonna have a scenario on which you'll see cracks on the tension side. It means, for example, at this region. Excuse me. This region of the brain. Because why I'm showing at the bottom, because that's the tension side. All right, that's first thing I want to say here. But you are good on the left and right because the moment is less than your applied moment is less than your threshold of cracking. All right, okay. So let's see. As the load is further increased, these cracks quickly spread up to the vicinity of neutral axis and neutral axis begins to move upward. All right. So what we are saying here is that as the concrete starts to cracks at the bottom, all right, so this neutral axis will shift up. Because why? Because it is a separation between tension and compression side. As it's just like pushed up by this, why? Because this cracks are going higher and higher in the cross section, right? The cracks that shape. Let me show you one. Let me just draw it here. All right, this is your original neutral axis, let's say. All right, so you start to see cracks here, 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 and here. Okay. So what is happening? When you are cracking this much, the concrete left would be this portion, the clean concrete. All right. So for this one, neutral axis is going to go a little bit higher. Okay. As the cracks move higher, okay. So it does what? What does it do? It just again makes, sorry. All right. Pushes the neutral axis even higher. All right. So this tendency would be kept doing until you're just totally crushing and you're reaching to this top region. Right. So the neutral axis would be shifted up. That is what we're talking about. Because why? Because the cracks are going higher and higher, causing the cross section, your healthy cross section to be smaller, shrunk and shrunk. Okay, that is a topic. That was this note that I gave you at the end. All right. So let's continue. All right. Now let's go to the ultimate strength stage. All right. So what is going on here? At this point, you're over that 50% of a prime C region, meaning what? Okay, this was your prime C, correct? So it tells you that if this was your elastic region, okay, 50% of prime C. All right, now you are in this region. Your stress is more than 50% of F prime C. You are at the nonlinear region in a way. Does it make sense? In a nonlinear region. All right. Tensile cracks moves upward, as I just described you at the last slide, as does neutral axis, correct? Assume the reinforcing steel has yielded. All right, so also steel yields. Okay, so let's see. If I want to give you a status of what's going on, look at this beam. Okay, so the cracks has extended a lot. Okay, they're reaching top and ultimately crush the top surface. Crush compression concrete. That would be how the concrete fails. Your cracks reaching that high that reach the top surface, or in other words, compression concrete, and crushes that. Now the concrete fails, the whole structure will fail. Okay. All right. So let's look at the stress and the strain configuration here. So here we are dealing with the strain. All right. So this is your final strain, ultimate strain of concrete on top, right? That's what we are assuming, correct? On the neutral axis, nothing. And then continue to have the epsilon y for steel. Does that make sense? Now there also, so what we are assuming, we are saying the strain reach to yield the strength of a steel. For concrete, it reach to ultimate strength of concrete. Okay. By the way, do you remember this number was 3000? Remember that? Ultimate strength of concrete to be 3000. Usually, that's what we assume. All right. This is a strain. What about the stress? So the relation between a stress and a strain here shown in this graph, right? The stress and the strain shown in this graph. All right. So if you want to look at it, does that make sense for you if I say it is here on top, right? It goes a little bit higher to reach this point, like here, right? And then it goes to this point, like here, and then reaches to 0. right? The concrete stress strain, the relation between stress and strain would be in this shape, as you're seeing, because we want to include the whole thing all the way to the 3000s. All right. So, but this is for the stress, right? Does that make sense for you if I say, all right, the distribution would be like this, goes like this. Okay. This is your stress in concrete. It is nonlinear. Why we are selecting this? Because this is a behavior, how the behavior is. Because we are including the whole all the way to 3000s. That's why it is not linear anymore. Okay. For what is going on for a steel? For a steel, you are reaching to your yield strength, right? Yield strength of steel. This is the yield. This is the yield strength. This is yield strain. Oh, strength. You can also call it the stress. To distinguish the two. All right. So now this shape is telling you the value of the stress at any level that you want in concrete. All right. Where it is coming from? It is coming from this graph. It's coming from this graph. Starting with the maximum on top, reaching to 0 on neutral axis. Okay. All right, so for the time we have for this session, let's look at a little bit of information about what's going on with this, with the remember as we are increasing the load. All right. Okay. So as we discussed before, this is your widths. This is your effective depths. This is the height of the section. All right. A steel cross section. All right. So you're increasing the load. This is the first stage. Concrete not cracked. Concrete not cracked. All right. So here what's going on? At this point, your compression or tension is the concrete compression or tension stress is less than your modulus of rupture, right? It is not cracked, or M applied is less than M cracked. Okay. So what happens is what we went through, right? So you're having a straight all the way. Okay. This is the uncracked phase. Uncracked. All right. So as you can see here, the tension side especially less than FR. So we are not cracked yet. We increase the load. Right, we are increasing the load. So at this stage, as a second stage, concrete, or sorry, tension concrete begins to crack. All right. So at this point, I would say I want to add the information for it. Almost you are at FR. I would say let's put it in this way. All right. So you are cracked at this point. Okay. So when you crack, what happens? On tension side, you're equal to FR. The concrete is equal to tension on concrete is equal to FR. All right. So a bit of nonlinearity you're seeing in concrete at the bottom, because it is at the moment of cracking. All right. Next one is concrete cracks. So here is CR or crack. All right. So on this one, you will use WSD or ASD method that we discussed. Okay. So crack section. So epsilon S is less than yield yet. So your steel hasn't yield yet. So FC practically is linear, although it is not showing linear, but it is assumed to be linear because it's like so close to linear behavior at this point. Okay. So tension is more than your FR. Fs for a steel less than yield at this point. Okay. So for this one, let me wait for the one before. I can give you some space to write here. Concrete in tension is neglected due to crack, but still is still there. Okay, this would be your cracked situation, cracked stage, I would say. Okay. So from this point, you are also seeing this illustration here. This illustration. Here we are just trying to show you an equivalent compression force, which is a summation of all this compressive stress. And also here is equivalent tensile force. Let me write. All right. Well, what are these symptoms? They are saying that instead of a whole compression block, I'm showing one force, which is the area on the or the volume of the so this is the equivalent force for the whole volume of compression, area of compression, depends on this is 2D or 3D, the way that you're looking at the problem. So that's it. That's as simple as that. So so this case, the fourth case, it is a case of yielding of a steel, but epsilon c is less than epsilon u. All right. So the steel has yielded, right? But the concrete hasn't reached to the to this crushing point. So this is the next stage. You're increasing the load, increasing the load. The first thing you do usually is to yield this, yield the steel at the bottom. So yield this first, right? Then on the next one, you're gonna yield also and reach to the crushing of the concrete on top. So this is usually how it goes. You are cracking, then you move to yield the steel, then you're gonna move up to crush the concrete on top. So I'm just gonna simply write on top of that, yielding the steel. Okay. And then the last one would be the ultimate strengths design. Neutralizers has moved all the way up slightly, and moment arm has increased. Moment capacity increases slightly. All right. So what happens? First of all, you became totally nonlinear. All right. Your steel has reached the yield strength, Fy, right? Your concrete has reached to your ultimate. So I would say here, let me erase the bottom. Okay. So how we can understand this good though? The problem is that we are having a problem understanding this nonlinear behavior, right? It is hard to capture, for example, the area under this curve. Because if it was linear, we're going to go with the triangle and find the area and find the C as a result, right? Do you remember the concept of the C, compressive force? This is coming, that's the equivalent value, just coming from the area. It's coming from measuring the area under your distress, all right? So we are having a problem. What we do for this, we're going to talk about this in the next session, right? We use an equivalent system. of a stress and strain. All right. We're gonna say, okay, instead of dealing with this curved unknown situation, right, we're gonna use an equivalent block as a compression block, right? We're gonna say its height is 0.885 F prime C. So its intensity is height to be A, that we're gonna calculate, we're gonna learn about it. All right. And there is a C as a compressive force that we discussed. That is equivalent compressive force, right? Same as this guy and same here and same here. Okay. Now you have the T. Okay. Just quick thing here, I forgot again. Epsilon U has reached to between 3,000 for concrete. Okay. So from this configuration of C and T, compressive and tensile forces, you can find a moment. How you can find it? You can using this moment arm between them to find. All right. What would be the distance between them? If you think about it, this height is D, right? This height is D. Okay. So if I want to find this height, it means from this point to this point. And you know that since I make this one rectangular, so the C is going to pass through A over 2. So meaning what? Meaning this distance would be A over 2. Whatever the A is, we're going to talk about more what is A, right? But that distance would be A over 2 for sure, because that's rectangular. And C is the equivalent for that, right? So it's going to pass through the centroid of the area, exactly. So if the whole thing is D, that portion on top is D over 2, what is left at the bottom? D minus A over 2, right? That is the moment R. That is the distance between moment R, between C and T, which is going to be used to find the moment strain of cross section. All right. So a few topics we're going to talk further. Do not get confused if you didn't understand it totally. First, what does it mean to find this rectangular shape? What is this to make it equivalent to this curved stress block that you had? How could we do that? All right, that's something we're gonna talk about it more. And this A concept, what is this height? How you can calculate it? We're gonna talk about that further as well. And for sure, how to find the moment and use the moment R. That's something we're gonna talk about more. All right, thank you. That's it for today.